Series circuits. In this video you will see what a series circuit is, and you'll learn how to calculate the equivalent or total resistance in a series circuit, and you'll apply Ohm's law to find the current and also the various voltage drops in a series circuit. And so you'll be able to completely analyze a series circuit and also see where the faults might lie within a series circuit. Remember when you see the pause video sign to do just that, and take great notes. Before we dive into series circuit, let's take a quick review of Ohm's law. Remember that Ohm's law has three different forms. One is that the current is equal to the voltage divided by the resistance. Another form is that voltage is equal to current times resistance. And finally, resistance is equal to voltage divided by current. And so these are going to become very useful as we analyze our series circuit. Series circuits now. Series means one thing right after another, kind of like the World Series is a series of games played one right after another, or a series of events. In the series circuits below, you can see that the components are all in series, one right after the other, around one path of a circuit. Notice that the electrons don't get a choice and will have to flow through every component in the series circuit. So right here, again using conventional current flows from positive around to negative, and this long battery terminal is the positive side, and so the electrons will have to flow through this resistor and back to the battery. There is only one path for current to flow. That's probably the biggest idea of series circuits. Now the problem with that is that if a bulb in a series circuit breaks open and opens circuits here so current cannot flow through it, it's going to stop the current everywhere in the circuit, because remember, electrons are stacked up bumper to bumper here all the way through, and so these electrons can't move forward unless these electrons move forward. So this bulb, even though it's perfectly fine, won't light because this one has broken open. The current everywhere in the circuit is going to stop. There will be no current. And that's why these kind of Christmas lights are quite frustrating, because if one bulb burns out, then they all go out, and it's very difficult to find which bulb has burned out. Let's start by looking at the current in a series circuit. Coming down to our circuit right here, we know that the battery does work to separate the charge and create a potential difference and a voltage, and that voltage is what drives the current around the circuit. In our conductors, the current flows easily, but in the resistance, where the material is stickier for the electrons and holds on to the electrons a little bit harder, it actually creates an impedance, or slows down the current flow. And again, it's easy in this conductor, but then it's difficult in this resistor, and then it's easy all the way back. So the parts that are limiting the amount of current flow in this particular circuit are these resistors here. And that's what's moderating the amount of current flow itself. Since the resistances are limiting the current, let's see how we can calculate the amount of resistance in a series circuit. Because there's only one path for the current to flow, all of the charge needs to move through each of the resistors here. And so if you asked an electron by the time it got back to the battery how much resistance it went through, it would say, well, it went through 2 ohms here, don't feel much in here, went through another 4 ohms, don't feel much here. And so it would say, hey, I felt 2 plus 4 ohms, I felt 6 ohms of resistance. So to find the equivalent or total resistance in a series circuit, you simply add the amount of the resistances in the circuit. So another example over here, again, easy to flow to this point. Feel 100 ohms of resistance there. Easy to flow here. Feel another 50 ohms for a total of 150. Easy to flow here. And then another 220 ohms and then we're back. So if you add them all up, 370 ohms would be the equivalent or total resistance. So let's go ahead and calculate the current in a series circuit. Coming down to our series circuit here, we know through Ohm's law that voltage is what drives the current and the resistance is what opposes the current flow. So if we're trying to find current, I is going to be equal to V divided by R. And in a series circuit, since the resistance overall that the voltage source feels when it's connected to the circuit is the sum of the resistances, then we would take that 6 ohms in our equation for Ohm's law. So I, if we have V and R, we can use this form of Ohm's law. I equals V over R equivalent. The total voltage over the total resistance is going to give us the total current. And so we get 12 volts divided by 6 ohms is 2 amperes. And that's how you can calculate current in a series circuit. You add up the resistors and then divide the voltage by that equivalent resistance. You try this one. Never compromise with honesty. Do the whole 7-step problem, including the drawing circuit, before going on to the next part of the video here. What current would flow if a 6-volt battery were in a series circuit with a 4 ohm resistor and an 8 ohm resistor? Come back when you're ready. How did you do? Well, if you had your 6 volts and when you add up the resistances here you had 12 ohms, I is equal to V over R. 6 divided by 12 is 0.5 amperes. Hopefully you were successful on this. Next, let's take a look at what's driving that current through the circuit. Of course, we know that the battery's overall driving the current through the circuit, but what happens is the work that this battery delivers is being used across each of these resistors. Remember, voltage is across. So this it's easy for the current to flow through this conductor, but when it gets here, it takes work to drive those charges through. But you can't use up all 9 volts of work per charge for your first resistor. You have to leave some for this other resistor. In fact, the amount of work per charge across these resistors is going to split up proportionally with the amount of resistance that there is in each one. So let's go ahead and do the calculations to see how much voltage we'd have here and here. We've seen how we can calculate the current, so that's going to be our first step. If we have a 9-volt source and our equivalent resistance is 45 ohms, then we can find the current. 9 volts divided by 45 ohms is 0.2 amperes. What we know about a series circuit is the current is the same everywhere. So that 0.2 amperes is flowing the same everywhere around. So we have 0.2 amperes flowing through 15 ohms, and we have 0.2 amperes flowing through 30 ohms. So if we use our other form of Ohm's law, V equals I times R, across a particular component, so this voltage V1 is just across this resistance right here. And this voltage V2 is across this resistance right here. And those are called voltage drops. Well, taking a 0.2 amperes and multiplied by 15 ohms and getting 3 volts, we did 3 volts of work per charge to move the current through this first resistor. We had 9 volts to start with. We used 3 volts, and so what must be left is 6 volts. And if you take the 0.2 amperes and multiply by the 30 ohms here, it does equal 6 volts. And if you look at the 2 voltage drops, 3 volts and 6 volts, and you add them back up, of course, you'll get back 9 volts. The voltage drops add up to the source voltage. They're called voltage drops because we start with 9 volts from here all the way around to here. And we dropped 3 of them, so we're left with 6. And that's a little bit about voltage drops and how you can calculate those in a series circuit. All right, you get to try another one here. We have a series circuit with a 120 volt source, and we have 2 resistors. What are the voltage drops across these two resistors? We have a 15 ohm resistor and a 5 ohm resistor. Give that a shot and come back to the video when you're done. Let's see how you did. You have a 120 volt source and you have these two resistors. So the first step would be to find the current. And we know that I is equal to V divided by R. But this is a total voltage and a total resistance because we just have the one path for current to flow. So 120 volts divided by 20 ohms when you add the two resistors together gives us 6 amperes flowing. Well, we have 6 amperes flowing through this 15 ohms, so we can find this voltage. V1 is equal to I times R1, so 6 amperes times 15 ohms is 90 volts. So we started with 120 volts, we've used up 90, so that leaves us with 30. But we can also do this with Ohm's law. V equals I times R. So 6 amps times 5 ohms is 30 volts. And again, the two voltage drops are going to add up to the source voltage. So, in summary, with our series circuits, we see that there's only one path in a series circuit, and therefore the current is going to be the same everywhere in series. And since there's only one path, the total resistance is found by adding up all the resistance in the circuit. And then we can find the voltage drops across each resistor that are going to drop proportionally to the amount of resistance there is. And these voltage drops have to add back up to the source voltage because this is all you had to start with. And we also saw that in a series circuit, since there's only one path, if one bulb burns out, then both bulbs will turn off because there's no path for current to flow, and the current would be zero regardless of where you look in the circuit. And this is called an open circuit. So, great job. That was series circuits. And Scratch's parting comment. I think that's a little bit of a stretch there, Scratch. But I do hope you're serious about striving for continuous improvement.